In the last video, I talked about linear equations, and I made the argument that sometimes you'll be given a linear equation in sort of an ugly form like this, and it's often useful to take that linear equation and solve for the variable y. You'll always be able to solve for the variable y unless you have a vertical line, which we won't be super concerned with in our class. And when you're able to solve for the variable y, you'll always have two terms, a linear term and a constant term. And that's guaranteed because in order for it to be a linear equation in the first place, each of your terms had to either be constants or linear terms. And if you're solving for y, all the linear terms with x's in them will be over on the other side of the equation. What I'm trying to say is when we solve linear equations in our class, they'll always end up in the same form. They'll be y equals some number, maybe I'll use the letter m to denote that number, times the variable x, plus some other number, I'll use the letter b to represent that other number. And getting equations into this form, this y equals mx plus b, or slope-intercept form, is more than just a useful way to see the different solution pairs. It actually allows you to come straight to the graph of the linear equation itself. Both the m and the b in this equation give you information about the graph, and using that information, we can sketch the graph, and that'll be the purpose of this video. Let's first focus on the b. The b is the number that's all out here by itself. It's not attached to, loosely speaking, the x. In this equation up here, the b was the number 2. Think about what that tells you. If the value of x is 0, then it doesn't matter what the value of m will be equal to. This term will always take on a value of 0. So when x is equal to 0, what I'll be left with is y equals b. What I'm saying is the value of b is just the solution for the y variable when the x is equal to 0. If we think about this more geometrically, recall that x is our horizontal axis and y is our vertical axis, so the value of b will always tell me what the height, the y-coordinate, should be when the x-coordinate, how far left or right I am, is 0. It'll be the height that the line crosses this vertical axis, and that has a special name. This vertical axis is called the y-axis, so the height at which the line crosses the y-axis is what's called the y-intercept. The value of b in y equals mx plus b form is always going to tell you the y-intercept. We saw that up above, right? In this form, the value of b is equal to 2. And note that if you look at my graph right here, it goes through this point 0, 2. It intersects the y-axis at a height of 2 because the value of b in y equals mx plus b is equal to 2. So suppose I had the equation 3y plus 2x equals 12. Sure. This is definitely a linear equation because each of my terms are either constants or some number or coefficient times a variable, either x or y. But it's not in slope-intercept form. To get it into slope-intercept form, I need to solve for y. So maybe I'd subtract 2x from both sides of the equation, giving me 3y equals negative 2x plus 12. Then divide both sides of the equation by 3, and I get y equals negative 2/3 x plus 4. A couple of comments there. When I subtracted 2x from both sides, I could have written 12 minus 2x instead of negative 2x plus 12. Those two things are equivalent. However, I chose negative 2x plus 12 because I knew I was trying to get it into this form. Similarly, when I divided both sides of the equation by 3, I could have written negative 2x all divided by 3, but I instead wrote that as negative 2/3 times x. I chose to write things this way so that I could tell what the m was equal to in y equals mx plus b. Anyways, this linear equation 3y plus 2x equals 12, written in slope-intercept form, is y equals negative 2/3 x plus 4. So my value of b is equal to 4, and my value of m is equal to negative 2/3. Because the value of b equals 4, I know that the y-intercept must be equal to 4. I know that a solution pair happens when x equals 0 and y equals 4. So later on when I want to come up with my graph, I better make sure my graph goes through this point right here that has an x-coordinate of 0 and a y-coordinate of 4. We've talked a lot about the b in y equals mx plus b, but we haven't talked about the m in y equals mx plus b. To understand the m, the way I like to think about it is b is kind of where I start at, loosely speaking, and m is telling me how much I'm going to change by, loosely speaking, as the x value increases. So over here, when x equals 0, we already know that y is equal to 4. But x isn't always going to be equal to 0. What if x increases up to 1? Well, then instead of just having a 4, I'm going to have a 4 plus 1 of these negative 2/3. What if x was equal to 2? Well, then my y value would be equal to 4 plus 2 of these negative 2/3. If x is 3, I get 3 of these negative 2/3. What I'm saying is, each time I take one step to the right on my graph, each time my value of x increases by 1, my value of y is going to increase by whatever m is equal to, negative 2/3 in this case. The slope always tells you how much y increases by each time x increases by 1. So in this specific linear equation here, each time x increases by 1, y increases by negative 2/3. And because that happens each time x increases by 1, I could think about this as if x increases by 2, y increases by 2 of these negative 2/3. Or if x increases by 3, y increases by 3 of these negative 2/3. And that actually ends up being an easier way to think about these, because when x increases by 1, y increases by negative 2/3. If x increases by 3, y is going to increase by 3 of these negative 2/3. But 3 times negative 2/3 is just negative 2. So instead of thinking about the slope as how much y increases by each time x increases by 1, even though that's entirely true, it's easier to think about the slope as a fraction, tells you how much y increases by on the top divided by how much x increases by on the bottom. A lot of books use the phrase rise over run, meaning this graph should rise, go up by negative 2. Each time it runs, goes to the right by 3. I don't know, maybe that helps. Maybe a little bit more concrete is the slope always encodes the change in y divided by the change in x. If you've never seen this notation before, these triangles are the Greek letter delta, and they represent the change in math. So let's tie this all together. I know this point 0, 4 is on my graph. The slope tells me how much the y-coordinate increases each time the x-coordinate increases by 1. So if I take one step to the right, my y-coordinate should increase by negative 2/3. In other words, go down by positive 2/3. Down by positive 2/3 leaves me somewhere in here. That's hard to see exactly where I end up. Maybe I should do it again. If I take one more step to the right, I'm going to increase by negative 2/3 again. In other words, decrease by 2/3. That leaves me somewhere over here. Still hard to figure out where I am. So maybe I do it one more time. If I take one more step to the right, I'm going to increase by negative 2/3 one more time, and that takes me down here to this point that has integer coordinates, that has an x-coordinate of 3 and a y-coordinate of 2. We could figure out this point is on my graph by applying our first interpretation of the slope 3 times, but what might be a lot easier is to apply our second interpretation of the slope, that the slope encodes the change in y divided by the change in x. Because the slope as written as a fraction is negative 2 divided by 3, from this point I go down 2 units and right 3 units to get to this point. You could do that again to find more points on the graph if you felt like it, down 2 units, right 3 units, etc., but you don't need to, because you know that these are linear equations. So once you have 2 points on the line, you have the line itself. That's a lot of talking, but there's some really important concepts encoded in here. Let me do a quick example for you. Suppose you had 4y minus 8x plus 5 is equal to, I don't know, negative 7. Sure. First, you can recognize that this is a linear equation. Secondly, you can recognize that this linear equation is not in slope-intercept form, but it's easy enough algebraically to get it into slope-intercept form. Want to get the y's all by itself? Let's first subtract 5 from both sides. So I got 4y minus 8x equals negative 12. Then let's add 8x to both sides of the equation. I got 4y equals 8x minus 12. Finally, divide both sides of the equation by 4, and I get y equals 2x minus 3. I'm now in y equals mx plus b form, and I can recognize that m is equal to 2 and that b is equal to negative 3. Because b is equal to negative 3, I know my y-intercept must be negative 3. So I come down here on my graph and mark the y-intercept to be equal to negative 3. The slope is 2, but it helps to think about the slope as a fraction. So 2 divided by 1. Now I can view it as rise over run. I'm going to go up 2 units each time I go 1 unit to the right. So up 2 units, right 1 unit. You can continue doing that if you want, but you don't have to, because once you have 2 points, since you know this is a linear equation, you've completely defined the line. This line represents this linear equation. It also represents this linear equation. And if I wanted to write things in function notation, I could say f of x equals 2x minus 3 as a function shows up with this graph. And just like we can get the graph from the equation, we can also come up with the equation just from looking at the graph. And it doesn't involve any new information. You stare at this graph. You recognize that this graph goes through the point 0, 6. In other words, it has a y-intercept of 6. In other words, in y equals mx plus b notation, the value of b would be equal to 6. What about the slope? Well, the slope is defined to be how much the graph goes up each time I take one step to the right. That's hard to tell. I don't end up at integer coordinates here. I can't tell how much I went up, some negative amount because I went down, when I took one step to the right. However, you might recognize that this point appears to show up on the graph with integer coordinates, 2, 5. And to get from this point to this point, I rise by -1 units, go down by 1. And I run by 2 units, I go to the right by 2. So therefore, the slope must be equal to -1 divided by 2. In other words, -1/2. If you know m and b, you can immediately come up with the equation y equals m, -1/2, times x plus b, 6. Any solution to this equation will show up on this line. If you stare at this equation, you might recognize that when x equals 4, for example, 4 times -1/2 is -2, and -2 plus 6 is +4. So when x equals 4, y should be equal to 4. A solution pair for this linear equation is 4, 4. Note that 4, 4 on my graph shows up right here, and sure enough, that's a point on this line that represents all the solution pairs of this equation. There's a little bit of review on what's referred to as slope-intercept form, or y equals mx plus b form. It's going to be the standard way that we write linear equations, and it's going to be super useful in this class.